to introduce this. That's always confusing. I'm pleased to introduce this session on electricity tariffs. So sadly, it's the last concurrent session of this great conference, which in a sense makes life pretty easy to me because everybody knows the drill about sessions now, so I don't think I have to explain how it works. And the good news is, since it's the last session, we have very motivated people. So I'm sure we're going to have like very lively and interesting discussion. And to make things even better, it's a 2-hour session. We have 3 papers, so we'll have plenty of time for lively discussions. I do encourage presenters to try to stick to the official drill, so to try to have a 20-minute presentation if possible, so that there is more time for discussion. However, since we have time, I'll only warn you if you go well beyond that. I'll start warning you at like 25-ish minutes, so that because we have like technically 40 minutes for everybody. So try to stick to the 20 minutes, but don't get too stressed out about it. So without further ado, our first talk is by Clément Cabot from ParisTech. So please take it away.
Thanks a lot. Can you see my slides? Perfect. So thanks for giving the opportunity to present the paper. I will discuss the research I'm currently doing with Manuel Villavicencio from PSL, which is about second-best electricity pricing in future power markets. And we've tried to develop an approach to evaluate the benefits and consumer reactions to future tariff design. So first, let me introduce you with a bit of motivation. We have now in Europe lots of countries that have performed their smart meter rollout, especially in France. Also in the US, it has been almost done. And what's really great is that we now have the opportunity to get very fine data on temporal consumptions of electricity. And this can allow us to send price signals to the end users so that they can shift their consumptions to time in point where electricity is cheaper or more polluting or less polluting. So it will now become mandatory for retailers to have at least one dynamic price contracts in the retail market, at least for big retailers. That's from the European agreement that will be live, I think, in 2022. Yet, elasticity of the demand is a very common assumption in power markets. So if you look at power prices, especially in markets where you've got lots of PV, such as California or in the US, the market price really change a lot during a day. You've got periods around noon where it's almost set to 0 because you've got lots of PV. But then the issue is that right now for the consumer, it's very flat. So either a flat tariff here in yellow, or it's 2-part with on-peak price and off-peak price, which really captures great the evening peak demand, but not really send price signals to say if it's better to shift the load here at night or is it better to shift it during summer period. So also in France, we've got lots of newspapers that are discussing if it's interesting or not to be on peak, off peak. Apparently, it's too expensive for most consumers, so that better switch off to something very flat. But on the other end, we now have retailers that propose to have real-time pricing. We also seen in Texas last winter that it was quite expensive to be charged the real-time pricing for some period of time. So there is some concerns about it. So the starting point of our research is this context, and more precisely, we've took the number of the European Parliament that indicates an annual saving of 22 to 70% of the energy supply component in their annual bill for small consumers. So as you know, I think the bill is composed of many different expenses, and energy supply is around 1/3 of it. But still, it's huge saving potentially too, and it should indicate that we should switch to more dynamic pricing. And the context is also to understand how increased renewable generation and increased carbon price can increase or lower the benefits of dynamic pricing, because we will have much more time periods with near zero marginal price, and the peaking price will be more and more expensive. So the 2 research questions we're trying to answer is are if the current rates are well suited for the evolution of power markets, and if the consumer are elastic enough to see bill saving materialize. To do this, I will explain to you quickly the framework of the research, so the two models that we're using and the first results. Also, it's quite research still in progress, so don't hesitate if you've got any suggestions or amelioration that you foresee. Quickly on the literature, we've got quite some work that already have been done using either star design model or more mathematical optimization. And usually we can see that benefits are quite low in this literature and are mostly on the long-term benefits of having price reactive consumers. Because of course you can curtail the load in peaking time, so you lower the need for investments in peaking technology. So that's interesting. On the field of empirical evidence, we've got some research paper also from Faruqi, Volak, or Alcott that are more based on pilot projects and try to assess to what extent consumers are reactive, also depending on their social characteristics. Also pilot projects, I haven't indicated it here, but the low carbon London is a real also experiment in London that show how users react to dynamic prices. Finally, there are some econometric works that tries to estimate the elasticity of consumers to electricity price. So mostly it's annual or biannual elasticity because of the data and the measuring that was performed before, but now we start seeing also estimates for more real-time prices. In a nutshell, the results, so we think that the current residential time of use doesn't provide the right incentive with an increasing share of renewables, because it doesn't allow the users to benefit from the low PV, the low price linked to the PV generation in the future. So probably it's not well suited and should evolve. And then, of course, real-time prices delivers increasing benefits with more renewables and carbon price, but it's quite low in our central scenario of elasticity compared to the savings that are envisaged by the European Commission. Also, the model reached 8 to 18% peak reduction when the prices are very high, and it quite compared to the numbers that are foreseen in the pilot project. So it quite reassure us. So now I will quickly go through the methodology. So very easily, we've got a first model that we allow us to determine the day-ahead wholesale market prices. So it's unit commitment. This anticipation of the market prices is passed to the consumers, which will react to the prices. And that's really the first step, most important. But then we also rerun the unit commitment model to assess the market impact. So it's a bit a way to stress a bit the assumption that we make that consumers are price takers. So yeah, the unit commitment model, the objective function is to minimize the cost of producing electricity, but considering the range of different production units. So we try to include quite some details because we want to use this unit commitment model as a proxy to determine the wholesale market price thereat. So that's why unit commitment was important. And so the objective function has 3 different sections, let's say. The first one is really the short-run marginal cost of producing electricity. So the variable cost, a premium for the carbon price, we're considering the emission factor of the different units. And then we've also added a markup in order to reflect a bit the heterogeneity in the production unit. So I won't discuss this really inside the slides, but we can discuss it later if you want. It's just that we try to approximate the best we can the merit order in France. Then there are some costs associated to the unit commitment. So it's more like startup cost, and it also comes from the literature. And then the value of first load. There are also some assumptions, of course, with this model. So the firms will offer all of their available capacity on the day-ahead market at the short-run marginal cost. So we don't consider any strategic bidding or market failure on this at this level. Yeah, and also there are, of course, also some more subtleties that are not perfectly represented, such as for code generation, for example. And so we take the marginal value of the supply and demand equation, and this is our proxy for the market price. Then the second stage, we've got consumer response to the market price synthetic. And so they all have a reference demand, and then they react with respect to their willingness to pay, or so this is the estimate that we took for the flat retail tariff that would have been proposed to them. So it's just a demand weighted average price of electricity that they would see during the year. And so if the prices are higher, they will tend to underconsume, and if the real-time prices is below, they will tend to overconsume based on their elasticity. We also don't consider cross elasticity, and this we can discuss afterwards also if you want. Yeah, I will quickly go through the data, but not too much. So it all comes from the NSOA transparency data for load, renewables, in-feed, per exchange capacities. Also from the literature for the unit commitment cost, for example, from Shield, or the operation and maintenance costs are taken from the European Commission GRC. And yeah, also lots of data from the Open Energy Modeling Initiative. I can only recommend if you don't know it. And then in terms of scenario, with the starting point is 2018. And we've considered the increasing share of renewables for different scenarios. So I won't discuss all of them right now, but so of course, when you increase 3 times the CO2 price of 2018, you reach current levels. And here for the renewable installed capacity, so I'm speaking only on PV and wind, you reach approximately, I think, the targets of France for 2023 or 2025, so it's quite short term. Then in terms of load, we've taken Enedis open data. So it provides aggregated consumptions by segment, residential, professional, and industrial, for different voltage level at an half-hourly granularity. So we've mostly considered the residential, the tariffs that were under flat rate. So that's our baseline, but also additionally some profiles that are under on-peak, off-peak to stress the current time of use tariff. A bit of illustration. So here on the left, you can see the average consumption of a residential consumer in France, depending on the day of the week and the hour of the day. So you can clearly see the evening peak demand and also the peak demand at noon during the weekend. Also very little consumptions during the night. What's interesting is it's to see this for consumer that is under the time of use tariff, so residential still. And you can clearly see a shift of consumptions towards the night. So usually you've got some appliances that are directly like automatic, such as water heater, but you've got also, I don't know, like a washing machine or laundry that can be switched towards those hours. So yeah. Finally, on elasticity, we've made quite a literature review, and we find estimates in the US for Brook and Abaya-Sakara, but for each segment, but we've mostly performed sensitivity around this to see the impact on the results. So again, some illustration. Here we can see in yellow the market prices, in blue the evolution of residential reference demand. And so in red, you've got the adjustments of the consumptions for low values of elasticities, and in green here for higher values of elasticity. So 4 times the default values. So I think elasticity here should be understood as something a bit more wide than just reacting to market prices, but it's more like elasticity of the households to market prices, and you can assume that such distortion of the load are feasible only with heavy automated appliances and also storage, basically, like electric vehicles or something like this. Yeah. So that's it for the introduction, and now we can dig a bit into the results. So the first results is to check if the users that are under time of use with what it takes in terms of demand adjustments are still profitable. So in the with using historic prices, we can see that the price that they're captured is globally lower than the one that's user under the flat tariff capture. It means that they are consuming at time point where electricity is cheapest, and that's also quite reassuring. It means that they're consuming during off-peak periods, so quite logically the price should be lower. But what we can see using the model and increasing share of renewables is that such interest lose interest with the increasing share of renewables. It's even becoming positive with for the residential segment with the scenario of a doubling of the renewables and 3 times the carbon price. It's mostly because such tariff doesn't incentivize people to shift their load to noon, basically, during the timing point where there are lots of PV. So it's quite also called the fact that with lots of volatility in the market prices, it will be very hard to determine such on-peak, off-peak periods, because basically it can change all the time. And there is a nice paper from Astier that speaks also of this. And that's the first learning of the research. Then for the real-time prices gain over the time. So of course, a user that is reactive to price is able to capture generally lower prices than the interest. And we can also see that under our different scenario with increasing share of renewables, it's more and more interesting. So that's results we expected, of course, but it also means that but we also see that we are quite far from the results that were envisaged by the European Parliament. Maximum we reach -5% in the last scenario, and it's very little compared to in terms of bill impact. So of course, that's also because our first central assumptions is quite low in terms of elasticity. You have seen that it changed little the consumption pattern. So what happens if we increase a bit the elasticity of the end users? So here are the sensitivity we've performed, multiplying the elasticity each time. And so, of course, with increased elasticity, you can see that the interest of having real-time pricing and being able to react is more and more wide and big. And we're reaching, almost 20% here in this scenario, which is close to what the European Parliament have envisaged. Also, there is something I haven't discussed yet, but given our modeling framework, what we have a bit implicitly is that the consumers won't consume less if they are under real-time prices. Because as you react to your average price, it mostly offset in the end. So there is no change in terms of annual consumptions. And so we haven't the details of the calculation made by the European Parliament, but we believe that a huge price rebate like they've advanced are maybe also linked to a lower annual consumptions. And this, of course, would also needs to be a bit investigated to see what it means in terms of loss of comfort or utility of the consumers. So that mostly it, what I wanted to discuss today. To wrap up a bit, we find that the current residential time of use doesn't provide incentive that will be of interest with an increasing share of renewables and carbon price, that globally we see interest in real-time pricing, but quite low, and that also is quite aligned with other research that show that on average for consumers, it will be less than 5 or 10% of the bill that will be impacted by switching to real-time prices. And yeah, also in terms of peak reduction, it's at maximum in the central scenario, we reach 8 to 18% compared to the baseline, which again is quite aligned with the literature. And just to get a bit of a sense of it, if we assume that all the segments of the residential and professional segment would react to prices, it would lower the demand. The peak reduction would be around 3 gigawatts, which is still important, but of course it would take a lot if we assume that all the flat of the consumer that are under the flat tariff would react right now. And also what's interesting is that we've seen that it doesn't necessarily coincide with the system peak load, because of course it depends on if the market price is at its highest during the peak load or not, but prices and demand will be less and less correlated, because it will be more net demand that will be correlated with the prices in the future. Yeah, and yeah, I was just then comparing this to the literature. And in terms of future research, where mostly we'll expand a bit the scenarios to check the results for more mid or long-term scenarios. So 2030, for example, in terms of renewables and carbon price, what it would mean, and also potentially also check what happens if we also reduce the share of the thermal units, or if the price of the gas or the coal also increase, if you can gain even further interest and peak rebate. Thanks a lot for your attention. I think I should be around 20 minutes, and if you have any questions, it's the time.
Yeah, great. You're perfectly on time. Great job.
Thanks.
Is there any question from you? I have plenty of questions, but I'll just let you audience have an opportunity to ask questions first, or if you need time to think, I can ask the first question. All right. Go ahead, Lito.
I think James Carroll was first.
Oh, sorry, go ahead, James. Sorry.
Thank you very much for the presentation. I thought it was really interesting. Just in terms of, I guess, you know, looking at households and looking at how, you know, effects could be quite heterogeneous across household types, for example. Is there any research done in terms of the types of households that will be switching to these more flexible contracts, and the types of households that are inherently more flexible? And is there any way to model in different types of households into your analysis? For example, the retired or the unemployed or the working from home, which is all of us these days. It would be a lot more elastic than, for example, a busy family that works 9 to 5 and leaves the house every day.
Yes, thanks for the question. So there are some study. I think no, so here I'm on the annex. The one from Gambardella, for example, he assessed bill change for 74 German residential load profile, and he mostly found that for 80% of the bill, there will be very little impact of switching to dynamic prices. So there are some study already. The framework that we've made will definitely be able to accommodate different load profiles and see. So, but what's really hard to have is rather the elasticity of the consumers, because when you look at project pilots, you see that basically it changes also depending on the day of the week or depending on the season, and of course different households that don't have the same electric appliances wouldn't be able to do as much arbitrage as others. But more generally, I think a common result from the literature is that the more wealthy the household is, the more flexible he will be, because he has the opportunity to invest in electric vehicles or even home batteries. He usually has a lot of different electrical appliances, and he's maybe also less captive of his working hours. Or we can think to teleworkers right now. They, yeah, in a way they're more flexible because they can always arbitrate, because they're already they always at home. But on the other end, they will also be captive to work and have their screen online all the day. So yeah, I think it
Super,
kind
thanks
of,
very much. That
yeah,
was great presentation. Thank you.
thanks.
So now, Victor, I guess.
Yeah, thank you. So my first question would be just for clarification quickly. The savings you presented us in the tables were annually, right? Table 4 and 5.
Yeah, annual savings only on the electricity production component of the bill.
Okay, thanks. And then I've got two questions, maybe comments. So one is related to potential endogeneity between the electricity price and the demand shifting. I mean, if you have enough load shifting to switch off 3 nuclear power plants, you might see changes in the spot market prices, but then again would maybe change the load shifting behavior. Is there any chance to incorporate that into your model?
So that's something we've considered. So what we've done is that the first step is to get the market prices, they read, then the consumer reacts. That's more or less the framework that is envisaged. And then we've rerun the market prices, a unit commitment model, with the shift of the consumptions of all the users. And so in the base case scenario with low elasticity, what we see is a very little impact in terms of market prices. I think it changed like maybe 1% change. So these price taker assumptions, we've tried to stress it a bit. Of course, for a higher level of elasticity, then the change are way bigger. And so we haven't done it yet, but we can think of like more of an iterative process, because of course in the commitment decision, the producer will also incorporate the fact that some users might react, and so it will of course change the market prices. So that's correct in terms of remark, and we've tried to analyze this too.
Okay, thanks.
We also have a question by Christine. Go ahead.
Yes, hi. Thanks for the presentation, Clément. My question relates a bit to what James asked as well, so about different appliances. And have you considered splitting the elasticity according to appliances? So might be that not like a household has not the same elasticity for all the appliances. And also, like I guess it's more relevant to switch like the huge loads like heat pumps and EVs, and the other things are not so important if the elasticity is low for those. Yeah.
Thanks for the questions. Good point. We think of this, so to split the household's demand, for example, in the different, like for heating or for electric appliances, and associate a different elasticity for each one. The point is that we had quite scarce data on this. So if you know good source of data to be able to do this, I'm really interested. Also, we found more like model-based synthetic profiles that really stack up the different hues, and you can even personalize the household, saying that he has each equipments. But that it's more like for further research, we would like to investigate this a bit more indeed.
Yeah, thanks.
Thanks.
Okay, Jai, sorry.
A question, maybe.
I think we still have 5 minutes. I do have also a couple of questions. I have 2 questions on the pricing of on the models that generate prices. So do you, I didn't get, so you increase renewable production, but do you change anything else in the park? Like, do you assume that some gas plant exiting or not, or something like that? And also I'd be curious to, you said you might talk about the markup, so I'd be curious to have you thought about what's in there. Is it a transfer? Is it some non-competitive behavior? Well, and then I have a couple of questions also on the tariff part, but maybe these two first.
So the first one, it's about the unit commitment where we increase the share of renewables, but not the others. So yeah, as I've said, for now, we've just focused on the analysis of an increasing share of renewables and carbon price. What we're currently preparing is also additional sensitivity where we wouldn't change only those two, but rather also the thermal production capacities, so gas units, coal power plant, and also the nuclear share in France, because it might be important and might quite change the results as well. Because for now, it's really a huge 75% of the production, so it quite set the price. No, it doesn't necessarily set the price, but it's important to investigate the case where you've got less nuclear. So that's undergoing. And the second point, it was about the price markup. So, so it's the rationale for this is an article of I think it was Ward and Green that show that in most unit commitment model like this, you take quite default assumptions for each power plant, meaning that all the coal power plant fleet will be more or less the same, and all the gas fleet also you usually distinguish between CCGT or OCGT, but doesn't necessarily provide more aggregates. The point is, and maybe I've got some annex on this, let me check, that when you look at historical prices, no, it's frozen. Yeah, when you look at, so here it's, I think it's quite old, but when you look at the market prices that results in France each years, so you can see that it's quite progressive. And for each time of point, you're more or less able to know which unit was marginal, and therefore has a proxy for the real short-run marginal cost of the unit. So what we try to do is to more or less refine a bit such merit order. So that's what you can see here in yellow. It's the nuclear, for example, to get best estimate of this merit order. So it's also a methodology that we're trying to refine a bit, because a lot of those market prices are not set by unit in France, but are set by unit in Germany or Spain or in the UK. So you have to eliminate a lot of those points. And then using historical data, you're able to know which unit we're producing when. You still have issue, of course, because some units are what we call must run. It means that their commitment decision is not based on the purely merit order stack, but they have to run because they're just next to an ArcelorMittal factories, and there is a pro purchase agreement or something like this. So that's the markup that that's how we estimate the markup. We try to better a bit the outcome of the prices, because the issue with unit commitments, I mean, even unit commitments, you've got very low volatility of market prices from your model compared to historical results. And we're quite afraid that such low volatility of market prices could undermine the value of future technology that operate inside the market. So it's true of demand response, of course, but it's also true for batteries, because as you've got very little volatility, you can't really have market arbitrage of storing, destoring, or for demand response to take benefits of it. So yeah, I was a bit long. I hope it's more clear now. But yeah, please to discuss also such topic if you want after.
Yeah, I also have a couple of questions more on like the technicalities of France. So it's better if I follow up online, and perhaps we can move on to the next presentation, unless there is a pressing last minute question from the audience.
I would like to ask you, I'm sorry I can't raise my hand, but I have a question about your merit order model. Is it possible with this kind of modelization to capture negative prices, or your lowest marginal cost is 0?
Yeah, so it's feasible. I don't think we've seen it with the level of renewables that we currently have, because yeah, it's not enough to really yeah, take the whole generation. But we also didn't consider any feed-in tariff, and usually in such model the market price, when it's negative, it's equal to the feed-in tariff because you have to pay it to renewables, and this we don't have considered. But in theory you could have situation where some units are forced to produce if they want to be online, because you've got binaries of commitments for each unit. So you might see such effect, but we don't see it in the current model.
Okay, thank you.
All right. Well, thanks for the very interesting discussion.
Thanks a lot.
And great presentation. So thanks, Clément. And let's move on to Victor now. Who's coming virtually from the University of Kassel. Hope I pronounced that correctly.
Yeah, can you all see the slides in full presentation mode? Perfect. Okay, so thanks, of course, also to give me the opportunity to present to you my current research. It's joint work with Julia Freier, also PhD here at University of Kassel. I mean, and the title is Dynamic Electricity Tariffs, Designing Reasonable Pricing Schemes for Private Household. You might see some relations to what we just heard by Clément. However, we have a completely different perspective as we look from the household side on dynamic tariffs and on the characteristics of these tariffs and what they need to fulfill. Now, as I see that we have a group of experts here concerning dynamic tariffs, I can be really quick on the motivation. You know, there are several advantages associated with dynamic electricity tariffs, which are grid stability, the reduction of CO2 emissions, also the better integration of renewable energy sources, but also in terms of economic efficiency when it's that the prices should reflect the social marginal cost of production. Also here, of course, dynamic tariffs or time varying tariffs are more efficient than static or flat rate tariffs. Still, consumer preferences for dynamic tariffs are low. In fact, they are negative. There's a lot of studies that show that households really need a large saving potential to actually prefer dynamic tariff over a static tariff. And therefore, there are several adoption barriers that need to be overcome for households to actually implement dynamic tariffs, and also for widespread implementation of dynamic tariffs in the residential sector. Now, we believe that there are two main drivers behind the motivation of households to take a dynamic tariff. The first one is the financial one, so the savings. And there are two findings I want to point out here. First, the Charles River Associates, they investigate the effect of time of use tariffs, and they show that a price ratio of 1 to 3 or larger between low price time and high price time is only that ratio is sufficient to enable enough cost savings for households to actually participate. And also when talking about high and low prices in real-time prices, Faruqi and Sergiki show that actually the price spread between these high and low prices is decisive for the amount of electricity that is shifted, and also affecting the likelihood that people respond to the prices. And at the same time, enhancing knowledge about environmental benefits is greatly reducing the minimum savings that households require to participate in a dynamic tariff. So if they are aware of the environmental benefits and that they are participating basically to help the environment and reduce the CO2 emissions, they might need much less savings. Unfortunately, due to time constraints, I cannot stress the environmental topic in this presentation, so we'll focus on the pricing, but come back to that in the discussion if you like. Now, based on this motivation, we have two main research aims. And as I said, we look from the household perspective. Now the first one is how large must the short-term price spread actually be to yield enough savings for household that they overcome the adoption barriers and that they actually take a dynamic electricity tariff. And the second one is that we, during this, want to quantify the CO2 emission reduction potential that results from households actually participating in demand response caused by dynamic tariffs. Now, to do so, we start basically from scratch and design dynamic electricity tariffs. And here we use different input factors that can be the price, the signal to give the price. We look at 2019 and take the German market as example. However, our approach is easily transferable to any other country or energy market. Having this dynamic tariffs, then we model case study households' consumption and their price response in reaction to the different tariffs, and that allows us to quantify the potential financial savings and also the emission savings. And based on these findings, we can then determine the short-term price spread that is actually necessary for households to overcome the adoption barriers, meaning that we present some variations of the electricity tariffs to enhance the savings potential, the financial savings potential of the households. Now, starting at the beginning, if we want to design an electricity tariff, there are a couple of principles that should be accounted for. And the first is what we believe is important. Revenue neutrality basically means that if the household is not responding at all to the tariff, he or she should have exactly the same costs in the dynamic tariff as in the static tariff. So to basically have a fair comparison level here. And then there are 5 principles pointed out by Dupont et al. The first 3, transparency, simplicity, and minimum volatility, are basically about customer protection and also customer acceptance. And then with respect to the tariff design, there's cost causality, which is then again related to pricing efficiency, so to actually reflect the social marginal cost of production, and cost recovery, which is related to the revenue neutrality argument that all costs associated in the process of energy production and delivery should actually or must be recovered. Now, you might see that there's a little trade-offs that must be made between these principles because they do not all work along. So if we have perfect cost causality, we would have prices changing within seconds in response to what happens in the market. And that, of course, would not be simple, might not be transparent, and of course would not be minimum volatility in terms of household perspective. So looking at the tariff, we need to make trade-offs between these principles to find a fair solution. Now, what we then do is that we construct these tariffs with 15-minute price intervals or time intervals. For the spot market prices, it's 1 hour because they are defined on an hourly basis. And what we do is that we look at the spot market prices, which are the day ahead prices of 2019 in Germany, but we also look into the residual load and the renewable, the share of renewable energy production. And even though we take the values of 2019, we use forecasted values, which were forecasted 1 day before to then quantify or determine the price of the day. And methodologically, we built upon the normalization approach, which was proposed by Freier et al. 2019. I don't want to go into the details about the equations here. We can do later if you like. I will just show what they do with 2 figures. So essentially, these 3 input vectors that we just saw, I'm not sure if you can see my mouse. Yeah, perfectly. So we have the residual load, the spot market prices, and the share of renewable energy production. And we have this over the entire year of 2019. And we normalize these values between values of 0 and 1, so that they basically reflect the actual pattern of this vector over the entire year. Now, what we then do is that we transfer this pattern identically to a dynamic tariff, so that this is basically reflecting what we had before on the spot market price or the share of renewable energy production. And we account for the revenue neutrality assumption, which means that if you multiply this pattern with a load profile of a household, you have exactly the same costs as you would have when the household would have a static tariff, which is important for the tariff design. Now, having the three different dynamic tariffs, we can look into the households. And we assume really simple, to be honest, three different household sizes with different annual electricity consumptions. So the large one has 5,000 kilowatt hours consumption. And then we assume load shifting potentials of 5%, 10%, and 15%, which is basically a summary of what we see in the literature. We believe that 5% might be a little too low, 15 a little ambitious. So we, for the interpretation, we stick to the 10% values, but we calculate our model for 5% and 15% as well. What we also include in this approach is whether households possess a heat pump and a thermal storage. And we believe that this is important because heat pumps could and can react automatically to price signals, whereas households basically cannot, at least at the moment. And coming back to the discussion we had in the presentation before, we also only look at average households using standard load profiles, so we do not account for heterogeneity in households characteristics, which might be interesting, but unfortunately we don't do this. Okay, now what we see here is first the two lines. The dashed line is the electricity price of 2019, the average price for residential customers in Germany. And in the continuous line, you have the electricity price for heat pumps, which is slightly lower in Germany because they have reduced grid fees. However, the pattern for the dynamic tariff is identical. Just to quantify the savings, of course, we must account for the actual prices. And down here, you see the typical or the average load profile of German households across 1 week. And in these blocks, the consumption of the electricity of the heat pump with the thermal storage. So basically, when the storage is empty, it's consuming quite a lot of electricity, and then when the storage is full, it switches off and waits until the storage is empty again. Now, if we then model the response of our households to the price signals, we have a different picture. Now, I again only want to present this with figures. If you want to see the equations later, I'm happy for that. So what we do is that we assume households to be capable to shift 5, 10, or 15% of their consumptions 12 hours forward and backwards, which is maybe a rather simplistic assumption, but we believe it's suitable for what we try to look into here in our approach. And what we see is that the household is really consuming much more electricity when the price is low, and this repeats, of course, everywhere where you have low price periods, and consumes a little less than when the prices are higher. What we also do is that we restrict the maximum amount of consumption that is shifted into one 15-minute time interval to the amount that is already consumed in this time interval. So this should be maximum double the size of what is below. And we do this to avoid what others find as avalanche effects. When they model households' response to the electricity prices, they find that all consumption ends up in one single time interval. And this is simply implausible. And we try to restrict this by this modeling. And then again, for the heat pump, we see a similar trend. So this heat pump algorithm is the idea behind this is that it should keep the thermal storage charged or heated as long as the price is low, and always when the price gets lower in respect to 12 hours forward and backwards, it should try to charge the thermal storage, so use the heat pump and use electricity to avoid basically the high price periods, which is also happening quite well. Now, over the year, this leads to some financial savings for the household. And what I want to look into is the largest household with an annual consumption of 5,000 kilowatt hours. And we see that depending on the different tariff types, so here this is the price based on the share of renewable electricity production. And if we look at 10% load shifting capability, we see savings of roughly 50 euros. For the tariff that is based on the residual load, it's slightly lower, it's a little above 40, and the tariff which is based on the spot market prices is essentially much lower. It's even below 20 euros. I'll come to this in the discussion. However, we find it quite interesting to see that the spot market prices might actually not be the best signal, at least if you consider an annual period, to induce for time varying pricing. Now, what we also see is that the heat pump is essentially already capable to create quite a lot of annual savings. Again, depending on the tariff, it's a little less or more. Now, as you can see here, I call this gross financial savings because we believe that there are actually some costs associated with switching to a dynamic tariff. And essentially, we thought it's one-time investment costs, annual metering costs, and then the transaction costs that occur if you have to manually respond to price signals. You can also translate this as the loss in welfare associated to reacting to price signals. We said then, well, smart metering installation costs and also the metering costs themselves to be zero. This might be typical for the German case, but at least here the smart meter rollout, well, when it finally will come, will be mandatory. And also the metering costs will be mandatory so that households have to pay these anyway, independent of whether they have a dynamic tariff or not. So we do not want to associate these costs to the dynamic tariff. However, the transaction costs that households have, well, they only arise if you actually take a dynamic tariff. And then, of course, we have to account for them. And Rucamo et al. Perform a choice experiment where they basically quantify the minimum savings that households require to actually prefer a dynamic tariff over a static tariff to be 78 euros with a confidence interval of plus minus 14 euros. And we take this estimation as basically as target corridor where the savings over the year must reach, which the savings over the year must reach for households actually to be willing to take a dynamic tariff. And as you might have remembered from the slide before, even the largest household that does not reach this. Okay, so as I said, we then try to alter the tariffs in a way that this savings potential can be reached. And what we do is that we exponentiate the absolute values of the underlying input vectors to basically try to modify the distribution of our input variables without changing the order of it. If we would change the order, we would violate the principle of cost causality, but we believe that it's valid to just exponentiate these variables so that the pattern would look exactly identical, just with greater spreads here. And this is also what we see in the analysis. So we increase the spreads within a short time frame, which then allows larger savings. And what we then see is that if we look again at the household with a large consumption of 5,000 kilowatt hours and assume a load shifting capability of 10%, 12 hours forward and backwards, we see that the savings that the household gets over the year can be reached when the average short-term price spread, which is the price spread within plus minus 12 hours, if this price spread on average over the year is somewhere between, let's say, 30 cents, 35 cents, if you want to be on the safe side. So this is the amount of price spread that you need on an average daily for households to be actually willing to take a dynamic tariff, which is essentially quite a lot and might not be realistic. I'm not sure how I'm doing on time, but I think we have some time, so I will not skip the limitations and just present them. Of course, with our study we have lots of limitations that we must be aware of. So first of all, we assume fully rational households that always search for the minimum price. We also assume constant cross-price elasticity. We just heard before that households might, well, be more capable to shift consumption from day to night than other way around, or maybe if you have a working household, sometimes you simply can't shift consumption. again, we only consider average households, so we neglect that there are naturally winners and losers of participating in dynamic tariffs. Again, then there's also that we rely on stated preferences to quantify the transaction costs. There's lots of literature that argues that these might be overestimated. So we must be careful here. On the other side, we can take this as a conservative value to be on the safe side. What we are working on is data from 2017 and 18 as well to have a periodical or small panel to see how this is changing over the years. Yeah, two more limitations. We just assume that retailers will play along with these tariffs, and then we also exclude indigeneity between prices and demand response. Okay, last slide for me. General conclusion is that even really large households need price spreads, short-term average price spreads of more than 30 cents to generate enough savings to overcome the adoption barriers. And we believe that this is actually not really realistic, or in other words, that the manual shifting of electricity consumption yields limited reward, while at the same time causes substantial welfare loss. And in that way, as we also see that the heat pump is capable to create quite a lot of savings without having to shift manually if it's connected to thermal storage, the main finding of our paper is basically underlying the necessity of automatic price response devices with really high electricity consumptions for dynamic tariffs to be actually deployed widely. And these are heat pumps, electric vehicles, or maybe even fully smart home systems or so forth. And coming back to what we initially said, or what I wanted to basically exclude a little CO2 savings in our paper, we also estimate the CO2 savings that a household can get over the year if he shifts accordingly this 10% of consumption to the tariff. Naturally, the CO2 savings are highest if the electricity tariff is based on the share of renewable electricity production. On the other hand, because of the high correlation between this share of renewable electricity production, the spot market price, and also the residual load, households also save quite a lot of CO2 under the other tariffs. And if all households of Germany would have had a dynamic tariff in 2019, they could have saved up to 1 million tons of CO2 without accounting for merit order effects or other feedback effects. Yeah, thank you very much for your attention, and I'm happy to answer questions if you have.
Oh, thanks a lot, Victor. That was a very complementary presentation to the previous one, because you look at load shifting exclusively, and the previous presentation was looking only at home price elasticity. So I guess we're two sides of the same coin. That's very interesting. We do have a question by James, so go ahead.
Hi, Victor. Thanks very much. It was really very interesting. I just had I know a little bit about this literature, and it's something I'm hoping to explore a bit more. But it's my understanding that a lot of the previous work has looked at, for example, you know, these events that happen, for example, in California, and they might, for example, the trial might look over a year and look at maybe 8 or 9, you know, peak time events. And it kind of makes me think a little bit about your transaction costs and how much time households have to adapt to these changing prices. And I'm just wondering, have you any comment on that? Have you any assumptions in terms of how much warning households are given in terms of, you know, changing their behavior according to the forecast? Are we thinking about day ahead, or are we thinking about real time, instantaneous? Because obviously in a renewable based system, we can add an element of forecasting to these prices. Not really a question, it's a comment that I just thought maybe you might want to add to.
Yeah, thank you very much for this important comment. Now, in our paper, we assume that we work with day ahead prices for the export market, and to be comparable, we also use the forecasted values for the other two input vectors. And we here also use the values that were forecasted 1 day ahead. And we assume that this basically 24-hour before announcement is sufficient for households to be capable to shift then electricity consumption 12 hours forwards and backwards, which might be a strong assumption, but we believe that this 1 day ahead warning would be sufficient. Yeah.
Right. No, I'm just wondering if the transaction costs will decrease in the future, given that our forecasting is probably, look, we're in a day ahead system, so there's not much we can do about it, but it seems that there's much more we can do in terms of adding, you know, almost a weekly forecast in that weather forecasting and renewable forecasting is getting so good. It might significantly reduce transaction costs. I don't know, something to think about maybe for myself rather than you, but.
No, it's a really good point. And actually in this project where I work in, where we just conducted a choice experiment with a representative sample in Germany, where we do try to investigate this. So we try to make a choice experiment on dynamic electricity tariffs and ask for how much. So we have an attribute which is having for levels about how much previously they receive price information and for how long this price is then unknown, which is daily, weekly, and monthly, I think. And then this is really preliminary results, but we see significant difference between daily and weekly information, where people highly prefer the weekly information compared to the daily, and also would prefer monthly, where we then can consider whether this is still plausible. Is a different topic. And in terms of necessary cost savings, this then would translate into highly reduced transaction costs. So you're absolutely right about that.
Thanks very much. Great work again.
Thanks.
Yeah, maybe a couple of follow-up remarks on this transaction cost question, because there are a couple of studies that may be interesting to you. Like there is this RCT in SMUD, I believe in California, where they randomize whether by default or not you are in the real-time pricing option, and there is a lot of inertia. So it seems like it's unclear what is in this transaction cost to actually switch on a real-time pricing tariff, because if you put them by default, they don't leave, but if they have to opt in, they don't opt in. So it's unclear what's there. I also seen some recent working paper on New Zealand customers, where you see that basically there is a learning process with RTP, where you have to get used to the tariff to understand what's going on, and you are much more likely to like it if you learn a little bit about it. But yeah, having some sensitivity around this willingness to earn this transaction cost and what that means is a very interesting thing to look at. Are there any other questions? If not, I do have a question on your slide 11, I believe. I got the impression that basically the savings you get with your different scenarios are kind of linear in your peak shifting ratio. Like if you get 10%, it's twice what you get for 5. So maybe there could be some scope to have some other ingredient that make this relationship non-linear, and maybe the potential, it's more and more costly for you to shift, or there is some other story going on. Because right now the story seems very linear, and you could almost have a closed form. So maybe not closed form, but it seems that there should be some non-linearities going on somewhere, and I don't know what the right place to put it in the model, but yeah, I was wondering to have your thoughts on that.
Yeah, so first of all, you're right about the observation. It's almost linear. I don't know where I showed this or here, because of we kind of restrict the amount that is allowed to be consumed in one time interval. We have, for higher load shifting capabilities, less, so to say, in relative terms, electricity consumed or shifted into the optimal prices, and the rest is distributed around this minimum value. And so the savings are almost linear, but essentially this white area here is slightly smaller than this one, and this again is slightly smaller than this one. However, you're right, this is really almost linear, and we maybe should think of a better way to basically restrict the capability to shift electricity in this larger getting load shifting capabilities. Yeah, but we haven't really thought about that, to be honest. But maybe we should. Yeah.
Okay, thanks.
So just quickly on the load shifting potential, I don't remember the time frame that you considered where you're able to shift the load, but do you perform sensitivities on this? Like if you can shift only in a 2 hours time frame or 3 hours, 6 hours, how it impact the results?
Yeah, so we assume 12 hours forward and backwards. So okay, now we are stuck in all these equations. Here we did some robustness checks, and for the maximum load shifting period, now this is 12 hours forwards and backwards. This is 24 hours in total. So this is here. And then if we would assume 9 hours, the savings would be already a little smaller. And so basically we see here decreasing economies of scale, so to say. If we have a really small load shifting capability of, I think we assume here 3 hours forwards, backwards, the savings are, let's say, half or a little less than half of what we get when we have the entire day. And then if we would have 2 days, it's not so much more. So, but it's of course important to test all the assumptions that we make. That's right. Yeah.
And so just to clarify, so if you have a very, since it's symmetric, right? You say it's plus minus 12. So if you have a very low price in the, so you have an historical pattern which let's say consume at night. And so if you have a very low price in the middle of the day in between, you would charge both days the same day, or do you have a constraint that makes sure that you have some heat for for on both days and not twice as much heat on one day and zero heat on the next? I mean, I'm not sure if my question is clear, but
when you talk about the heating mechanism, then we would be for the electrical heat pump and the storage, right? So there we, I think I have this also here somewhere. Basically, we have in the red line the storage capacity or the state of charge. I'm sorry. So it's when the electricity is consumed, it's charging until it's full, and then again it's using electricity, heating until the storage is empty. Now, what we do is that when the prices are relatively speakingly high, so the normalized ones, we try to keep the state of charge lower than 20%, and as soon as it reaches 20%, it's switched off. And when the prices are relatively low, so again, this is the relative price within the time frame of plus minus 12 hours, then we try to keep the storage charged with saying when it's below 80% charging, it should again try to charge again. And thereby we basically ensure that it's not switched off 2 times, but basically it's a running algorithm looking forward. And also for the household, there's actually searching forwards and backwards, but of course only switching 1 time. That is ensured, or only shifting to 1 price period. I hope this was understandable.
Yeah, and for the storage, it was. For the household, I'm not sure, because if you switch on, so if so, can it be the case that on one day you shift forward and the next you shift backward, so that both load end up the same day, or?
That should not be the case, I guess. I mean, what we do is that we always look from period T. We search for the minimum price within a range of 96 15-minute intervals, and then we shift 10% of the consumption into this period. And of course, it could be that for one period T today, the minimum value lies tomorrow, but then for any period tomorrow, this would also be the minimum value, or at least it would be lower than anything in the day before. So it shouldn't be possible mathematically that what you just suggested, that I shift from today to tomorrow and from tomorrow backwards to today, could not happen.
Okay, thanks for the clarification. Are there any more questions, comments, or suggestions for Victor? well, otherwise, let's thank Victor for this very nice presentation, and move on to the last talk of this session by Christine from ETH Zurich. So Christine, take it away.
Yeah, thank you. You can see my screen, right? No, or yes. Yes, you can. Yeah. Okay. Yeah. So thanks for the chance to present here. I'm a PhD student at the Group for Sustainability and Technology at ETH Zurich. I'm working on the flexibility in electricity load from an interdisciplinary perspective. So I aim to integrate social components into energy system models. And the work I'm presenting today is about what type of incentives are required for households to provide flexibility with their devices, and what role do low carbon technologies play in this. Yes, I think there's not much motivation needed after the first two presentations, but what I would like to highlight here is that our focus is definitely on the households with low carbon technologies. So households owning heat pumps, EVs, stationary storage, and PV installations, because under the assumption that load shifting is most relevant for those appliances and devices. And a different angle on the tariff topic is also that we look at grid perspective. So far it was more about wholesale electricity prices and more on the generation side and saving CO2 emissions. And our perspective is more on the, especially on the distribution grid operators. So the devices like EVs and heat pumps, they likely increase the peak demand, and that's challenging for the distribution grids. And we look at that trade-off between, or what flexibility can do to avoid grid reinforcements and those investments. Yeah, so related to the other two presentations, this overview shows results from trials that investigated different tariff types. So on the x-axis, there's the ratio between the peak price level and the off-peak price, and on the y-axis, the peak load productions in percent. And now there are not all studies included because they do not always provide those two data points. But what we can see is that, yes, critical peak pricing, like the green dots, can reduce peak quite substantially. Also the real-time pricing, the blue dots, but at the same time, there are also very low blue dots. So if you compare this one with these ones. Yeah, and there might be a tendency that high price differences achieve higher peak reductions, but that's not very clear. But I mean, it's just a small sample, so it's hard to generalize the conclusions. But there might be many other aspects influencing the demand behavior besides the prices. For instance, the time of day, so flexibility potential is not the same throughout the whole day, and there are also uncertainties around the response of households, which then affects the system, especially related to grids. So this process of providing flexibility involves many different areas. There is the economics of the financial incentives, such as tariffs and saving money and earning money from providing flexibility. Then we have the social components regarding behavior and adoption of different incentive types. And of course, also the technical requirements. So building physics regarding how much load can actually be shifted from heat pumps, and also the electricity grids. Do they need to be reinforced, which then impacts the need for flexibility. And by combining these three layers, we hope to provide a holistic view on the flexibility provision. So the overall research question we aim to answer is, what are the potentials and barriers for flexibility provision of different low carbon technologies in households. We have 4 sub-research questions. The first 2 are more on the technical side. How do low carbon technologies affect household demand load? So the difference to the standard low profiles, basically. And what is the technical flexibility potential of these new loads? And then research questions 3 and 4, we aim to also incorporate the social aspects to find out how much of that technical flexibility potential is actually feasible to achieve. And those 2 questions are the ones I will focus on in this presentation. So how do different stakeholders perceive demand response with different incentives and why, with a particular focus on grid operators? And how does the diffusion of low carbon technologies affect the adoption of different tariffs with different automation laws? Yeah, so hoping that the devices like EVs and heat pumps will encourage the adoption of tariffs, and that's then a win-win situation because those are the loads we need to shift, basically. And to answer these questions, we apply a mixed methods approach. And to answer the 2 questions we're looking here in this presentation, we conducted interviews with different stakeholders and a household survey. So we are trying to investigate the system perspective, including retailers, service providers, and so on, but mostly grid operators. Then those interviews help to understand the potential benefits and existing barriers of the different tariff designs from a system perspective. But we did not aim to provide a statistical representativeness. So that's more focused on the different geographical areas of Germany. So our focus is on Germany and a wide spectrum of company sizes, especially for distribution grid operators. And then the focus on households, because they are the ones providing the flexibility. And the pilot projects cannot really say a lot about the adoption of tariffs because that's usually pre-specified. And we were specifically targeting low carbon technology owners to investigate this effect of these technologies on tariff adoption. So we included heat pump owners, EV owners, households with PV installations and storage technologies, as well as households with none of these for a control group. So the results from the interviews, when we talked to different actors in the system, we actually found they're not so supportive of tariffs. As this first quote says here, it's questionable if time-varying tariffs are the right instrument. And the doubts here relate to network requirements. So some networks need to be reinforced anyways due to PV installations or wind farms. And then there's doubt of how much flexibility is actually required. And this depends a lot on the geographical area. So in some areas in the north of Germany, they are rather happy if finally all the EVs are connected because they have a lack of demand in that area and the grids can handle it. So they don't really see a need for those tariffs. And on the other hand, if there is really a problem, the DNOs need to make sure that their measures work. So they cannot really rely on incentives that might work or might not work. And that's why they would prefer direct load control. And they think that more complicated tariffs than the two-phase static time of use tariffs are neither attractive for households nor for the grid operators. And on the household side, they think that households will not put any effort into this, so they will not adapt their behavior and might worry about planning insecurities, particularly related to EVs. So the mobility demand still needs to be met. But on a positive note, they don't think that there's going to be a problem with all households responding to the same price signal and then making the situation worse for the grids. So as you all know, there are different components in the tariff price. So there's also the debate about potential trade-offs between TSOs and DSOs, but also like wider system perspective and the local DSO situation and the peaks. So it could be the case that the price signals, if you combine them, they balance each other out. And that's what the DSOs are afraid of, basically, so they don't see a lot of value for that purpose. Concerning the barriers, only households who can afford smart meters can benefit from the time-varying tariff, which might increase social inequality. But that's specific to Germany. As far as I know, in the UK, for example, I think the government is paying for the smart meters, so there are different business models. And regarding the DNOs, they currently get support for reinforcing the networks. So they have little incentive to invest in smart solutions because they will increase operational costs. So that requires regulatory changes. And also the DNOs are responsible for the network operations. So of course, they prefer the most reliable option, which the tariffs are not. And on top of that, the small DNOs, and there are a lot of them in Germany, that's also different in every country, worry about their capacities. So making the billing process more complicated is not in their interest. So overall, the view not so positive. Now we're switching to the household side and the survey we conducted. We wanted to investigate the attractiveness of different combinations of automation levels and tariff types, including what decision criteria influence their selections. So we included 4 automation levels. Although it's likely that the response to the price is automatic, especially for those devices like heat pumps and EVs, people still influence the use of technologies by using override options, for example, or setting boundary conditions, like the temperature settings for heat pumps or the minimum state of charge for electric vehicles. And that's what we call semi-automatic. Automatic with exceptions, that's with the override options, and automatic is just fully automatic. Regarding the tariffs, we included an electricity saving tariff and a high load tariff. So the price increases with increased consumption after a certain threshold, either cumulative or at a specific time of day, if a household's own load is higher than a threshold. Then we included static and dynamic time of use tariffs, with the difference that for the static option, the time periods of different price levels are fixed, while for the dynamic one, the price levels are fixed, but they can occur at different times of the day. And finally, the most advanced option, the real-time pricing tariff. After data cleaning, we produced 280 responses for analysis. The sample is definitely biased towards full-time employed men with a university degree and an own house, but that's basically the people who own a heat pump and an EV and have TV installations at the moment. But interestingly, the age range is rather balanced and also rather old in the sense of over 30, which was also our target group. The household size is diverse. 58% of the respondents do not switch tariffs within 2 years normally. And some have also tested a smart meter or are currently using a smart meter, almost 15%. Regarding the technology mix, 46% of the households have heat pumps and 29% EVs. And on the right-hand side, you can see a split of all the different combinations of the 4 technologies of interest in our study. So heat pumps, EVs, PV installations, and storage. But we did not base our analysis on the detailed subgroups because the subsamples of each category are too small for that. So coming to the results, which are definitely preliminary, and there's a lot of analysis to be done. You can see that people owning both a heat pump and EVs, or only EVs, or only heat pumps, or none of these are listed here in that graph. And almost 40% of the people not owning an EV or a heat pump would not want to switch at all, while only 7% of the people that own both a heat pump and an EV did not want to switch. So technology seems to have an impact, and these results also should suggest that people owning an EV are more likely to select a real-time or dynamic time of use tariff. Regarding automation levels, the fully automatic ones and the ones with exceptions are most attractive across all tariffs, which is good from a network perspective because it provides more reliability. And also for the households, it's more convenient if they don't need to care about the prices. So that's what we discussed before about transaction costs. But they still prefer having an override option for certain situations. So especially regarding EVs, they just want to press a button and charge immediately in case there's an emergency or something like that. And we also found that people with smart meters are significantly more attracted to any tariff with automation. This might be because they already have required the equipment, so there are lower additional investments, or because they already have a good experience. We also asked the respondents for the most important reason for selecting a tariff, and this figure shows that across the technologies, saving money and doing good for the climate are the top two reasons. We also found positive correlations between the importance of saving money and the attractiveness of the high load and static tariffs, which could suggest that people think they can save money with those two tariffs. And people whose first decision criterion is climate friendly select real-time pricing significantly more often, and people want to who want the tariff to be simple to understand and want no changes in everyday activities are significantly more likely to not switch to any of the offered tariffs. And those reasons also relate to other information. So for example, the reason no changes in everyday activities is more important for people without smart meters, and those who switch tariffs more often find saving money more important. Beyond those reasons, which were actually significant for the tariff selection, we tested influencing factors, like other influencing factors, and we found that technology is the most significant one. And the results suggest that PV installations, EVs, and storage are the determining technologies for selecting a tariff rather than heat pumps. So if households do not have any of these technologies, they select the electricity saving tariff significantly more often, and also significantly more often not switch to any of the offered tariffs. Households with only PVs, as well as PV storage and EVs combined, select dynamic time of use tariffs significantly more often. And the combination of PV and EVs leads to selecting real-time pricing significantly more often, which is the most advanced one. The current tariff has also a significant impact on the selection. So households that currently have a green electricity tariff select static time of use tariffs more often, while households on a basic supply tariff select the high load tariff, and households with a heat pump tariff are happy with that and do not want to switch at all. And finally, we also asked people to choose between two different price ratios, and one was like a large difference and the other one was a small difference, and we found that households selecting the higher price difference between different tariff time periods are 3 times more likely to select one of the time-varying tariffs compared to the households that prefer the lower price difference. And that suggests that risk-averse people are less likely to find time-varying tariffs attractive. Yeah, so the key takeaways so far, like from this presentation, but so far from the analysis we have done so far, the DNOs see a reliability issue with the tariffs and therefore prefer direct load control. There are substantial geographical differences regarding how useful the tariff might be, and regulatory challenges might be required to incentivize the smart solutions at the grid level. Regarding the households, we find that saving money and a positive climate impact are the main reasons. Regarding technologies, PV, EVs, and storage rather than heat pumps affects the tariff selection. People with none of these technologies prefer electricity saving or high load tariffs, if they switch at all, which most won't. And risk-averse people are less likely to find time-varying tariffs attractive. And having an override option increases the tariff's attractiveness. And that's actually the challenge, because then the DNOs don't know when they will use this override option and how reliable the whole construction of the tariffs is for them. So overall, direct load control might be the best option for both the grid operators and the households. And as an alternative, simple tariffs might be enough and preferred by households. And future research should investigate whether, when, and how often the override option for the automation is actually used. So it could be that they just want to have it to make sure, but in the end, they don't really use it. Yeah, so that would affect the reliability of the flexibility provision. And also the future level of demand and supply of flexibility. Yeah, and finally, it would be interesting to investigate how different options for producing flexibility complement or compete with each other, like different technologies, also related to storage. Yeah, thank you very much. Yeah, I'm looking forward to your comments and suggestions.
Oh, thank you, Christine. Perfectly on time. You made my job so easy. Thanks a lot, guys. Is there any question from the audience? If not, I'm happy to start. Okay. I have a very not surprising question, I guess, from an economist. So you kind of show this correlation between different technology or attitudes with which tariff they prefer. So which of those would you consider, or would you deem are the most likely to be causal versus just caused by some selection bias? Or because you can say that people that have an EV are more likely to have some characteristics that also make them more likely to like dynamic tariff, for example. So it's kind of hard to disentangle. Are you capturing something else, or is it really the fact that you own an EV that you like price variations? So are you able to talk a little bit to that in your research design, like which relation you believe are really something causal, or which relation are more endogenous?
Yeah, that's basically the biggest challenge we had. So far, we mostly looked at correlations and just statistical tests, basically. So yeah, it's hard to tell, but I think also a lot of the things are related. So if we consider that EVs and heat pumps are adopted by specific people with specific characteristics, and then these characteristics are not really significant, we could have some conclusions out of that. But it's very hard to like determine the causal effects, I would say.
And I don't have an. I was just wondering if you could do something with because the correlation results are very interesting as well. Yeah, that's probably a question you get often with this presentation. So
yeah, but maybe if you have suggestions or anything like that, feel free to go ahead.
Not on the top of my head. I think about it.
Yeah.
I think Victor has a question.
Yeah, I had a question, but I mean, with the discussion you just had, I'm not sure if your sample size is large enough, but I mean,
yeah,
if you just go for a probit model or something similar, or I don't know whether you can try to like account for different factors at the same time to get an idea of that. And then my question also was related to the survey. I see from your abstract that you measured risk aversion basically by asking about the difference between high or preferences for high and low prices in the tariff. And I was wondering what other household characteristics or basically knowledge or preferences and so forth you ask for in your survey, because I believe that this is important and maybe also really interesting to look into, like political preferences or energy-related financial literacy and so forth.
Yeah, so we asked about whether their proficiency or education is related to the environment, to like get a sense of that. But I mean, if we look at people that have EVs or heat pumps, it's clear that the sample is biased in that sense. Then also like income and yeah, household size, also their job construction, basically, if they work at home or if they have like basically how their day looks like, if they have night shifts or something like that. Yeah, if they use smart meters. Yeah, I think that's most of the things we looked into.
Okay, thanks.
Yeah, we also asked them about their charging behavior and whether they use smart charging already, because that's basically what we were talking about. If we talk about tariffs specifically for EVs, it's basically like if you use smart charging and the price signal is integrated in the algorithm, basically. Yeah.
Okay.
I've got also a quick question. So I think when you presented the results of the survey and on the DNO side, you said that there was limited incentives for DNOs to deploy smart meter solution because it increased the operational costs. And I mean, it's not really a question, but I thought that smart metering was basically interesting for retailers, DNO, because they can access the smart meters from basically they don't have to come and to operate and to read the meter themselves and so on and so on. But maybe that's really just for retailers. But I wasn't sure why operational cost would increase with smart meter solution for DNOs. Just because they have to deploy it?
Yeah, good question. So it's not only about the smart meters, they would actually be beneficial for the DNOs as well, but to procure the flexibility from the consumers, they need like equipment to facilitate that. And that would increase the operational costs. And then there's like a, yeah, it's basically about the reliability of the flexibility. So the other option they have is reinforcing the grid, which is more expensive. But if they get support for that, then they still have the additional operational costs and they cannot really rely on the flexibility, then they might need to reinforce the grid anyways. And then they have double the cost basically. So that's kind of—
So their main worry is that, yeah, either you put direct load control and then maybe you've got also additional costs to pilot the households, but otherwise they're not enough confident that the response from household will be certain and fixed so that they can avoid to expand the grid.
Yeah, with the tariffs. So there are other concepts like tenders or auctions where they make the contracts in advance and so on. So yeah.
And have you also like discussed local flexibility markets or other flexibility option with them?
Yeah, so basically they prefer everything except apart from the tariffs. But regarding the local things, they fear also that's related to self-consumption basically, but in a bigger community. So they will use the grid less in the end basically. But the problem with that is that the grid is still required for emergency cases, like a very cold winter day, for example. So they still need to provide the grid, but no one is paying for it basically if they don't use it. So then they prefer things like capacity-based tariffs. So everyone still has to pay the network fees. Yeah, or the price will at the end be paid by the like poorer households that cannot afford the whole smart home system, and then they still need the grid and they provide it for everyone. Yeah.
Thanks.
Go ahead, Jane.
Hi, Christine, that was really good. I thought that actually more consumer-focused research really complemented the previous presentations. Just in relation to your survey, in terms of, did you capture, I'm sorry if I missed this because the doorbell rang during, I had to answer it, but the climate awareness and climate concern are obviously important aspects of the household and how they affect the EV adoption, heat pump adoption, and also their choice of tariffs. And I'm wondering, in terms of your survey, how were these aspects were they explored, were they captured, and were they and how were they included in the analysis?
Yeah, so we asked for what technologies they have. So, but that's like independent of their attitudes. And then in a separate section, we asked them about like their climate awareness, if their education is related to the environment in general. Is that what your question was?
It is. I guess it's in line with what's been suggested already. If you do have a chance to run a kind of a probit logit model,
yeah,
for this factor, it might be interesting to see what pops out. It's just that in a lot of our research on electric vehicle adoption, it's the key variable.
Yeah.
In our way, it's more important than many other aspects. And it just needs to be a consistent control within analysis like this, in my opinion. But just a suggestion, yeah.
Yeah, sure, thanks.
So I guess at this point we can also open a question to any of the presentations, since I think every speaker got the same time. So if you have like second thought on some pressing question in the previous presentation, feel free to go ahead. I also had a follow-up question on the household thing. So when I read the abstract of your paper, Christine, I was pretty curious about these preferences for override, because as you said, it's kind of connected to the DNO, and there's this, I mean, if you bother doing everything and then you end up in Texas winter and everybody override everything and it blows up, and you kind of, yeah, it kind of defeats the purpose. So but in the end, it seems in the survey it was not as high as I was expected, like the difference between override versus not override. So can you discuss a little bit what people answer exactly? Is it just a choice of tariffs with and without override, and you just look at the adoption, or do you have some specific question to understand what they are looking for in the override option?
Yeah, so we asked them about the boundary conditions for the semi-automatic version. So where they can set, for example, for an EV that the battery never goes below 30% or something, or if it's at 30%, it will be charged at any price, basically, like those kind of boundary conditions. And also for the override option, what they would expect of such an option. And I mean, the answers were quite simple, basically for like emergency cases, if they feel like they need to go to the hospital or something, then they want the car to be available. So it's really more about the fear that their technology cannot be used if they really need it. But because of their answers, we were thinking, okay, these are really just emergency options or situations. So it might be that they really want it, but in the end, they will not use it that often. Because, yeah, and especially if then, depending on how large the area is, that's also a bit of an issue for the DNOs. It might just balance out in a, like if you aggregate the effect, then if one or two people use it, it doesn't really matter. So yeah, the hope would be that it's really just emergency situations, but yeah, we would need to dig deeper into this. But that's really like a behavioral thing. So yeah, I think that would require like different elements.
Yeah, I mean, some of it is clearly behavioral, but some of it is also like some incentive compatibility thing, like all this like priority service kind of literature. So it's interesting to see that it does emerge as something statistically significant in what people say. So that's interesting.
Yeah.
It's hard to say, as you say, it's hard to say if it's just cheap talk. Of course, if you don't have to pay for it, everybody wants it. But then if you have maybe some tiered thing and statistical diversification will help. But I guess in the case of Texas, it doesn't really help because it's called for everyone at the same time.
Yeah.
Yeah, I thought that was a cool feature of the question to have.
Just a quick comment again, Christina, on your survey with the percentage share of people that choose a specific tariff. I think the least chosen was high load, which is the name that you use for critical peak pricing, I think. And what I find it interesting is that in the literature, usually critical peak pricing is the one that delivers the best peak load reduction, and seems like a good, like maybe an interesting options to consider to be a bit not real-time pricing, but not also fully static. So I'm wondering, yeah, if you can comment on the fact that it was very not chosen, and yeah, is it because it's too hard to understand or too uncertain? Because usually, yeah, or that the people with electric vehicles think it won't trigger enough savings for it to be really interesting for them.
Yeah, so that's yeah, like a good comment. We also were thinking that would actually be the ideal option, because every household just balances out their own consumption, and then we would have no problem. But I think the thing is that households more like prefer like a flat rate type of thing. So you have a specific connection and you can use as much of it as you want, basically, and then restricting the use of electricity at certain points of the day, which would be the points where the peak usually occurs, because that makes sense from the system. Then they would be restricted at those times. For example, in the evening when you like cook your meal, and you know when the actual peak occurs, and that's where they are least flexible with their electricity demand.
Yeah, and you maybe, yeah, you didn't include something like peak time rebate, so which is basically the same but the opposite. So you have saving if you shift your load, and usually it's household prefer it because, of course, if they don't want to do it, they don't have money. But usually it's also something in the literature that is favored. So is there a reason why you didn't include it? Or
so the normal price would definitely be lower than a flat tariff. So there are two different prices. One is like higher for if you go above a certain threshold, and the lower one is still lower than the baseline, basically. So they will have savings for the remaining time of the day, but they are not equally flexible throughout the whole day. So if you restrict them exactly in the morning peak and evening peak, that's what they are afraid of.
yeah, it's just that peak time rebate, it's like critical peak pricing, but instead of having an higher prices, you get a rewards if you shift your consumptions. So
Yeah.
it's also interesting for households, and usually it's they prefer it compared to critical peak pricing because it's positive.
But by rewards, you mean that they have
compensation,
like a negative price, or like not just because like the reward is basically that for the rest of the time the price is lower than usual.
It's on top of that.
Yeah.
So you have different versions of peak time rebates. So the one that got implemented in most places is you kind of determine a baseline, which is what you expect when people will have consumed, and you just give them some reward if they consume less than that, which was an incentive compatibility issue. But what you can do to make it incentive compatible is you can say, okay, if you really need electricity in the evening and you know you're going to consume 10, then you could have some kind of prepay this 10, let's say, spread out in your bill, and then you can still say people, okay, if you consume then less than 10, then you're going to get a reward on your bill. So that it's really a framing issue. There's a working paper by Loessl, I think. I'm not sure they published it in the end. But yeah, there is this idea that it might be, it's kind of this prospect theory, like losses versus gains kind of issue. And there is also this gaming issue that industry people or politicians also manage to give free money by gaming the system. But even if you make it incentive compatible, there is an argument, behavioral argument that people might prefer that.
Yeah, good point. Thanks.
May I just add on the question why people not really prefer the peak time pricing or the critical peak pricing? I was wondering how did you explain the different tariffs to them? Because of course this is important, especially when we look at surveys. That, I mean, if you, for example, used figures to explain the tariffs, and you have a really high price in the peak time pricing, that this is basically maybe the figure already looking threatening to the people, and then they don't really get the concept of this, but just react to the really high price in this peak. I was wondering whether you made sure that the explanations of the tariff is as simple and comparable as possible.
Yeah, that's definitely something we discussed a lot before we sent out the survey. Also with people that have no idea about tariffs. So it has to be understandable, but also as simple as possible. So we actually did use graphs, but tried to, like regarding the price levels, tried to align the base price basically. So none of the options is preferred just because of the graph, hopefully, but you can never be sure with surveys. And then we added like a text explaining basically what's happening, but as simple as possible. Yeah, but I mean, with surveys, there's always the issue that it could be that there was a misunderstanding or they misinterpreted things. Yeah.
Yeah, thanks. But I think working with graphs is a good idea here.
Yeah, hopefully.
Yeah.
Well, I think if there are no last minute questions, we can all use the 5 minutes to get a drink before the final plenary session and take a breath. So thanks a lot to you three. I really enjoyed the three presentation and learned a lot of things. And thanks for the nice discussion. It's really great that you took the time to discuss with each other, and hopefully you all enjoy it. And enjoy the last session of this conference.
Thanks a lot.
Yeah, thanks a lot.
Thank you so much. I just want to remind Christine to upload your presentation, please, on your dashboard. Thank you so much.
Thanks.
Okay, thank you so much.
Bye.
Bye-bye.
Thank you. Bye-bye.
Bye.